So I'm going to talk to you today about what we can learn. The title of my talk is what we can learn from photoluminescence imaging of silicon solar cells. And this was work that we did at IIT together with Dr. Ashok, Professor Arora, and myself. Okay, so this is the outline of my talk. First, I'm going to introduce you briefly to photoluminescence in silicon. And then I will ask, why is luminescence important in silicon solar cells? And some examples of luminescence imaging and conclusion. Okay, so two-slide introduction to luminescence. Supposing you have a semiconductor or anything in the ground state, and then you excite it. When you excite it, you create an excited state. So here it's the ground state. So now here you have one electron in the ground state, and this is the excited state. And now we ask this question: how does the excited state decay to the ground state? Okay, and I'm talking of solids and at this point in time, and they're not necessarily only of molecules and atoms. So it can do two ways. One is radiative, and the other is non-radiative. In radiative, the energy difference between the conduction bottom of the conduction band and the top of the valence band is the emission of the photon, and whereas in non-radiative, there are defects in the material, and the electron and the hole can recombine at the defect, and there is no light. So radiative means the solid, the sample exhibits a characteristic re-emission of light at a particular wavelength, and non-radiative means you only have heat and no light. Okay, and so we characterize this by a lifetime where tau 1 by tau r is the radiative lifetime. So in other words, the rate constant is 1 by tau r. So the rate at which the lifetime will be 1 by tau r. And then there's the rate constant 1 by tau nr for the non-radiative lifetime. And so the effective lifetime is 1 by tau f is equal to 1 by tau r plus 1 by tau nr. And I will keep coming back to this equation again and again many times during this talk. So I would like you to please keep this in your mind. Okay. Now, what is the efficiency of the luminescence? So that means I shine light. And what is the efficiency? The efficiency is given by, and that is by this term eta. The PL efficiency is given by tau r. So tau is effectively the effective lifetime, and tau r is the radiative lifetime. So you can see that the PL intensity depends directly upon the efficiency, and which in turn depends upon the lifetime tau. Okay, so this is another thing that I want you to remember, that the PL intensity depends upon the effective lifetime tau of the sample. Okay, so now we ask, since we had said that in the solids, the primary non-radiative recombination will happen because you have traps, we can make a simple estimate of what the non-radiative lifetime is like. So, you know, if you had n traps with a cross-section sigma, and if the thermal velocity is v, then 1 by tau nr, that is the rate constant, is proportional to this product nt times sigma times v, vth. So if nt is large, the lifetime is small. Okay, and so if you put in some typical numbers, sigma is 10 to the minus 14 centimeter squared, which is a cross section, and very low trap density as 10 to the 12 per centimeter cube. Please remember, it's extremely small. We are talking of 1 part in 10 to the 10 or 1 part in 10 to the 11 traps. The lifetime is of the order of 10 microseconds. So now, for a direct band gap semiconductor, something like say gallium arsenide, the radiative lifetime is for this doping is of the order of 1 microsecond. And so if we put down 1 by tau is equal to 1 by tau r plus 1 by tau nr, the same equation again, we get 1 by tau is roughly 1.1 into 10 to the 6 seconds. So eta, which is proportional to tau, the efficiency of luminescence is close to 90%. That's a good number. This is true for materials like gallium arsenide. However, for silicon, for the same doping density, the radiative lifetime is very large. And the reason is silicon is an indirect band gap material. So the strength of the matrix element is much weaker than for direct band gap materials. And so since tau r is so large, the effective lifetime is the same as the non-radiative lifetime. Oh, sorry. The effective lifetime is that of the non-radiative lifetime. So that means my eta BL is 0.01%. So this is very, very small. So you consider if you had a direct band gap material, we had close to 90%, and in silicon, it's an indirect band gap material. We have 1 part in 10 to the 4 is what my quantum efficiency is, and of course that's really proportional to tau. So luminescence efficiency of silicon is very small, and this is where the challenge of doing luminescence measurements in silicon is. And you should just remember that the luminescence intensity is just proportional to the lifetime. Okay. And I have a request, people, if they want to intervene in between to ask questions, please, you are most welcome. Okay, so that is the background that I wanted to do for understanding the rest of this talk. And it is sufficient for me that if you understand that 2 things, that the luminescence efficiency in silicon is small, 2, the luminescence intensity is proportional to the lifetime. These are the only 2 things that you need to take as a takeaway for the rest of the talk. Now, if you look at a typical solar cell, normally when you think of silicon, you think of microelectronics, you think of transistors, you think of packing billion transistors, trillion transistors in 1 centimeter squared. On the other hand, solar cells is an example of macroelectronics. A typical solar cell today will have about 15 centimeter by 15 centimeter, and this is just one device. It is not micro, it is macro, and this is one PN junction, and the size of this PN junction is 15 centimeter by 15 centimeter, and today people want to go over to bigger formats like 20 centimeter by 20 centimeter. Okay, so it's macroelectronics. This is what I want you to keep in your mind. Now, I want to just spend a couple of minutes on what is the IV characteristic of such a PN junction like this. Solar cells are made from PN junctions, and its simple IV characteristic is like this. In the dark, in the reverse, there's no current, and in the forward, once you exceed something like 0.5, 0.6 volts, the current begins to shoot up. And in this diode, if you go to about 0.6 volt, you have a current of about 9 to 10 amps because of the area. Okay. Now, when you shine light onto this, the IV characteristic is what is shown in red. The first thing to notice about the IV characteristic is the following. In the dark, the IV characteristic is in the first quadrant. In light, the IV characteristic is in the 4th quadrant. That means the current is negative even though the voltage is positive. And this is very important because the IV product in the first quadrant is positive, and that means IV is power, and that's dissipative. In the 4th quadrant, the product of IV is negative, and that means I have a power source. So it's very important. So the solar cell works because under illumination, the IV is in the 4th quadrant. So there are 2 or 3 important characteristics of this. One is at 0 voltage in the dark, you will have no current. But under light, at 0 voltage, you have a current which is quite large. It can be anywhere. For this particular cell, it's 5.5 amperes. For a little bigger cell, it can be of 9 to 10 amperes, minus 9 to minus 10 amperes. And this is called the short circuit current. And I'm going to use this word again and again many times. So the short circuit current is the current that flows at V equal to 0. And then the other term is the open circuit voltage. The open circuit voltage is when you apply forward bias, when you apply positive bias, there is, of course, this current is being generated by the light all the time, and let us assume this is constant. But then you also add this component of current. So when you add the 2, then at some voltage, this will cross the axis, and this is where the current will go to 0, and this is the open circuit voltage. So the open circuit voltage and the short circuit current are two important parameters of the lighted IV of a solar cell. Okay. And this voltage for a single cell is of the order of 0.6 to very high efficient cells, it will be about 0.75. And for ordinary cells which are commercial, it's about 0.63 volts or so. Okay. Now, I told you that we have this lifetime. What was this lifetime? The lifetime was when you shine light, you ask, let me go back here. When you shine light, you create electron hole pairs, and the lifetime is so you create excess carriers. And when you create excess carriers, the lifetime is excess carrier lifetime, and I will call that the same thing as the lifetime throughout this talk. The excess carrier lifetime is the average time these carriers are free before they recombine. Okay, and this lifetime, this excess carrier lifetime, we have seen that this is what determines the PL intensity, because that lifetime, if the lifetime is large and becomes close to tau r, eta PL can become 1. The maximum value of tau can only be tau r because that's a fundamental process. Okay, so the excess carrier lifetime, which is defined through this term tau, is a very important parameter in solar cells, and because it governs literally everything. It governs the magnitude of the short circuit current. It governs the open circuit voltage. So it also tells you how large is the open circuit voltage, is also controlled by this excess carrier lifetime, which is tau. Okay. It also controls the shape of this curve. In short, this excess carrier lifetime determines indirectly or directly the efficiency of the cell, solar cell. And I'll give you one example. So here is, so this is, you can see that here. So you can see, okay, what determines the magnitude of this VOC? And I'll give you one simple expression to sort of do this. I won't go into the derivation of this, but just take my word for this, that VOC is given by some term like this: KT by Q log JSC by J naught R, which is J naught R is the J naught of, J is equal to J naught e to the QV by KT. J naught is that prefactor, but this is the rate where all the recombination is controlled by radiation. That's what the R signifies, plus log eta PL. So you see, the VOC is, or the magnitude of the VOC is controlled by this log eta PL. And since the maximum value of tau is tau r, the highest VOC you get when tau equal to tau r. In other words, when it's a very efficient luminescence, a good solar cell is a good LED. This is something that initially came as a surprise to many people, but once you look at these equations, it is quite obvious that that is what it would be. Okay. So now let's look at some values for VOC. If you look at some technologies called don't worry what it is, most of the commercial technologies, which is a back surface field technology, it's around 630 millivolt. And then there are these days much better technologies available like PERC, TOPCon, HIT, etc., where VOC is of the order of 700 to 740 millivolt. So what made this big difference between 630 millivolt and 700 millivolt? It is the difference in the excess carrier lifetime. The BSF technology, the low voltage, has a small lifetime, excess carrier lifetime, that tau is only 50 or 100 microseconds. Whereas in these materials, it is milliseconds. I wanted to just give this as an example to tell you why people who do solar cell work are so focused on the lifetime, because the lifetime determines the efficiency of the cell. And you can see already here, it's a huge difference of the voltage of almost, you can get another 100 millivolts just by improving the material quality. So it's very important for us to continuously look at the material quality, to continuously look at tau and ask, what is the value of tau and how can I improve it? Am I doing anything to degrade it? And this is what the purpose of this talk actually is. So in a good solar cell is all about how to get and keep the highest excess carrier lifetime tau. So lifetime depends on, of course, the initial wafer quality, as we saw that. that if you should have very few defects, and even 10 to the 12 defects made your lifetime something like 10 microseconds. But also what is important is depends on how you handle it, what you process. So it is very important when you are doing some processing in a, let us say, a million wafers batch, you want to make sure that you are not doing anything to degrade the lifetime. And can you do this very easily? Can you do it in line? And these are some of the questions that we will ask. And this is what the purpose of this talk actually is. So what we want to do is, if I told you a typical solar cell is of this dimension, we want to get at every point on this silicon, we want to get lifetime spatially. Lifetime is a function of X and Y. How can we rapidly monitor lifetime over such a large wafer in a very small time? And that is what imaging is all about. Okay, so as I said, the photoluminescence intensity is proportional to tau, because that the recombination rate is given by the number of excess carriers into the background holes, if these are electrons. And then, so really speaking, PL intensity is proportional to tau, and there is G. What is G? G is the generation rate. That means that's just the amount of light you throw onto the sample. So I want to take out G and I only want to measure tau. Okay. And so one way of doing this is to image fast is to use an imaging method, and that can be done by a camera. So if we take, cameras capture whole images in very small times. So if we can image the brightness of the luminescence over the whole wafer, then we have actually captured and imaged the lifetime as a function of X and Y. So, so what do we need to do? First, if you want to measure tau, you measure the luminescence. In order to get luminescence, you have to shine light onto the sample optically. When you shine light, it creates electron hole pairs. And when these electron hole pairs recombine, they give you luminescence near the band gap. And you want to monitor this luminescence. Okay? So the first thing is to have an excitation source which can be done. So if you shine light, that is one way of exciting samples, creating electron hole pairs. Another way is, of course, by forward biasing a p-n junction. But only thing is now you need contacts, whereas optical excitation can be done without contacts at various stages of processing. And for imaging, we have to use a camera with enough sensitivity to capture the image at the frequency of interest, which in this case is close to the band gap of silicon, which is 1.1 micron or so. So here is an example of such an imaging system. So here is a sample is mounted on a chuck, and then you have two light sources. The light sources in this case are just a bank of LEDs, and you have two of them so that you make the light uniform all over the sample, because you must have the light uniform everywhere, otherwise non-uniformity in light will create non-uniformity in generation, and that will create non-uniformity in the intensity, and that will not be a measure of tau. So making it uniform is very important, and that is a design of the source becomes such a big issue. Then you have to have all kinds of filters, and here's the camera. The camera also has a filter. This filter is because I don't want to look at the light which is exciting the sample. I only want to look at light which is the luminescence. So I have a filter here which will cut off the light which is coming from the source, and only will see what the luminescence spectrum actually is like. Okay, so here is, for instance, let me give you an example. The luminescence of silicon peaks around 1100 nanometer in the infrared, and I'm going to use 600 nanometer to optically excite carriers from the valence band to the conduction band of silicon. So when I do that, and then I don't want to look at that light, I only want to look at this light, and that is the reason for putting the filters in front of the camera, is to cut out the light from the source and look only at this light, which is the near IR light. Okay. Now, as we already have seen, that one problem with this is that the luminescence efficiency can be very small in silicon, because it's an indirect bandgap semiconductor, and we saw something, it can be as small as 0.01%. So this is a problem, that the luminescence is very big. So this is the first difficulty we have when using a commercial CCD silicon camera. Now here is the camera. This is the quantum efficiency of the camera, and this effectively tells, quantum efficiency says that for every photon that impinges on the camera, what is the short circuit current? When the quantum efficiency is 1, I get 1 unit of current in the external circuit for every photon that comes onto the light. So at 630 nanometer, you can see there's a lot of efficiency of the camera, which I'm not interested in. I am interested at 1.1 micron, and you can see that the camera has very poor quantum efficiency of the order of 3% or 4%. The peak is at 1100 nanometer. There, the quantum efficiency is actually 0. So it's the product of the quantum efficiency with the luminescence of the silicon that gives us the effective efficiency of the signal to noise, and that is just this peak. This is all that I have to measure. So not only is the luminescence efficiency of silicon very small, but also the detector, the silicon CCD in this case is also very poor. So there are detection challenges. Okay, so I summarize that in the slide here. The silicon CCD has one big advantage. It's very low noise, because these days we make very high quality silicon cameras. On the other hand, the quantum efficiency is very small, and this is where the challenge actually is. Okay, so what I'm going to do is, so I have given you so far, I have explained to you why the excess carrier lifetime is important for solar cells. We want to map the excess carrier lifetime, and one way is that when carriers recombine, they will give luminescence, and this luminescence intensity is proportional to this excess carrier lifetime. And so we are going to use a camera, and so that we can capture the image of the whole sample at one go. And this is what makes the detection system very fast. So now I'm going to walk you through some examples and applications of such a thing. Okay. So what do we do? Let me repeat again. I excite the silicon sample at 630 nanometer, and then I look at the luminescence, which comes at 1000 nanometer, starts at 1000 nanometer and goes up to 1100 nanometer. But I have shown you that the camera does not have the response, and the PL intensity is proportional to the excess carrier lifetime. So if the intensity varies of the PL across the sample, that's a measure of the lifetime variation across the sample. Okay, so now let's see. Here let's look at this sample first. This one has an average lifetime of 500 microseconds. So you can see this is a piece of silicon wafer. You can see there are lots of bright spots, and then there are all these black regions. All these dark black regions are low lifetime regions. The bright regions are high lifetime regions. So if I put it on a proper grayscale, and I can actually say what is the intensity here, this lifetime is so much larger than this lifetime, and this of course are regions where the lifetime is extremely small. Here is another case of a sample like this. Bright regions have high lifetime, and the dark regions have low lifetime. Okay, but what we will do to make our life easy is to make a color map so that we can distinguish between different shades of dark and bright. And this is one such example. So here is a sample of multi-crystalline silicon. You know, multi-crystalline silicon by its very name means that I have grains inside them. It's not a single crystal. I have grains. So at the grain boundaries, there's recombination that will take place. So when I shine this red light to absorb, and then look at the emission, which is at 1 micron, you can see these regions. So on this scale, to read this graph, you say yellow here, yellow here corresponds to some arbitrary scale of lifetime, which is 50 to 60 microsecond. Black is low lifetime. So you can see actually these are regions of, by taking one shot, I have actually got a picture of the lifetime in different parts. Here's a very high lifetime region. here the region is about 50 microseconds, and this pink is of the order of 30 to 40 microseconds, and the black can be anywhere between 0 to 20 microseconds. So you can quantify how much is the defect zone, what is the high lifetime zone, the moderate lifetime zone, and this is very useful if you are in industry and you want to buy wafers and you want to quickly screen them without having to make solar cells. Okay, so you can see the advantage of this. And I give you another example. Here is a wafer that we had taken, and we had put done. It was a p-type wafer, and if you want to make a p-n junction, you diffuse n, in this case phosphorus. When you diffuse phosphorus, and then since you're diffusing to a whole large area of 16 centimeter by 16 centimeter, we wanted to see what the sheet resistance of the doped layer is in different places. And so we made a measurement with a Ford probe. We made these measurements, and then we took a luminescence image of the sample. You see that this sample has reasonably high lifetime, 50 to 60 microsecond, all this yellow region. But then at some periodic place, there are all these red regions which are low lifetime, 40 microseconds. What happened? These are the places where we made the Ford probe measurement. So you can see that the act of making the Ford probe measurement was sufficient to reduce the lifetime in those regions. There is no other way I would have actually been able to find this out. Okay, so probing the sample. So just tells us how careful we have to be to probe the sample. The next slide gives this in a much more graphic detail. So here was this was reported by Mr. Abbott in 2006. He had a wafer of silicon and he held it with a tweezer. Wherever you have X or plus, it is with the tweezer. And you can see when you do a luminescence image, wherever he has held it with a tweezer, it is black. The holding of the tweezer on a high lifetime sample creates defects and kills the lifetime. Whereas this was they had done this experiment because there was some water on it, they wanted to wash it off. So they blow dried it, so they held it to the tweezer. On the other hand, you pass it through a furnace, there's no holding with the tweezer, and then you can see that all these dark regions are actually not there. So just tells you how gently you have to be to handle these high lifetime wafers. And this is something you would never have known if we did not do this imaging. Another example, when they put many samples through a furnace, the first sample in the direction of gas flow, so you can see that the sample at the input end is very bad lifetime, so clearly some impurity is coming through, and as you go further and further out, this goes away. So you are actually having some impurities carried by the gas flow. Again, you can just see it by looking at this image. And what I'm going to give you now is how can we use this. So I have given you two examples. First, we have seen that you can have a distribution of lifetimes, and you can catch this distribution of lifetimes by taking an image with a camera, and if you variation in intensity is essentially the variation of the lifetime across the sample. Now this is on bare material. Now when you're doing let us say industrial lab and you're going to do some processing, so there are some examples from NCPRE which I will show. So there's a whole set of process. Don't worry about what all these processes actually are, but you can see that you could take a batch. If you go to industry, it will be typically a few lakh wafers, which will go through such a batch and through this whole process. Now, how do you know what you are doing at different parts of this process? And what I'm going to do is, at different parts of this process, I'm going to take out one wafer and look at the luminescence imaging and try to come to some conclusion as to what step is making it good and what step is making it bad. So there are 8 process steps, and the details of this process is not so important. So this was the bare wafer you started off with, and then there's something called saw damage removal. So then you texturize the wafer so that you reduce the reflectivity, and you see the lifetime is very poor here. And then you diffuse it. When diffusion requires you to put that phosphorus, this was p-type silicon, so you put down some n-type phosphorus and diffuse it through, you can see an improvement of the lifetime. But then there's an oxide which comes when you do this process and you remove the oxide, the lifetime has gone all over again. But then fortunately, when you heat the wafer, you can recover the lifetime, and then the finished cell looks quite uniform. So you see, we can see so if at each process, if we can understand what is happening here, we can remove these difficulties of processing, then we can actually end up with a material with much better lifetime than we started off with. So for instance, very easy, if you have 1 millisecond here, it's very easy to make it 10 microsecond here. But by looking at these processes, you can optimize and then say, I will use my this knowledge to optimize this process. So I'm just going to look at this part here. So after the removal, you can see the lifetime was very bad. But then when I did a 600-degree oxidation step, I passivated most of these impurities. So most of it is at the surface of the material. And so the luminescence has now, here the luminescence is mostly blue, which is very low, red is high. Here it is mostly red, and all this happened was I had to do a small oxidation step. Now imagine if you did not have this luminescence imaging, you would have to do many experiments, make full solar cells, measure it, and then say, sorry, this is good or this is bad. But now I don't have to make this full solar cell. I just do this experiment, change the temperature a little bit, change the time a little bit, and then optimize my process. This can be done much more faster and much more economically. And this results in, when we did this series of experiments, we found here with and without thermal oxidation, we could gain straight away a 5 millivolt. And you may think 5 millivolt is small. It's in this business, when you are competing for every millivolt, this is quite large. Of course, these days we get some 640 millivolt or so by tuning these processes. But look at the efficiency, jumped from 17.2 to 17.9. So this is very important. So the luminescence imaging helped us understand and to optimize the process. So I told you that, okay, now I'm going to go back to this equation where I told you when eta PL is large, that means when the efficiency of PL is large, that is when your open circuit voltage is also large. So here is an example of two samples. You can see this one has an open circuit voltage of 635 millivolt. This has an open circuit voltage of 631 millivolt. This is brighter than this. The bright means yellow is about 6,000 counts, red is about 4,000 counts. So you can see that this equation, this is just in line with this equation. So if you want to make progress, you have to make this 7,000, 8,000, 9,000, and then your open circuit voltage will keep increasing because your lifetime keeps increasing as you do whatever process you do. So this is the power of luminescence imaging. Without having to make a solar cell, the problems can be identified, corrected, and solutions incorporated in the solar cell, which cause significant savings in time and money. Okay. So I'm going to give you so what I'm going to do now is, let me see. Okay. I'm going to give you some different kinds of examples. Again, here is my solar cell. So when you look at it from the top, when you look at it from the side, this is the P-type material, and this is the N+, and this is the back metal, and this is the PN junction. Okay. So now, because we have these metal lines, there's a contact resistance, the resistance which comes because of the thinness of these metal lines, and also because there's a contact resistance. And when you have contact resistance in the, then I squared, currents are very large. So IR drops is very large, and I squared R heating also will take place. So you want to make sure that you have very low resistance in the cell. And I will give you an example of how luminescence, we can see where the resistance is large and how we can optimize it. Okay. So now I'm going to take you back to this cell. I told you there's a short circuit current and an open circuit current. When you short circuit, then all the current goes in the external circuit, and there's no current that goes through the diode, and so the luminescence should be 0. In fact, so if you take a luminescence under a short circuit, you shine light and you short circuit the cell from outside, you are drawing the full, all the carriers that are being generated are going into the external circuit, into a load or whatever, and so there's no luminescence. So in the short circuit, you should see a dark image, and that is what you see here. On the other hand, when you do open circuit, the current cannot go anywhere. All the generated carriers have to disappear only by recombination. And so this is the brightest image that you will actually have, so at open circuit. And then, of course, you have in between, you can draw different amounts of current, and you will see that the cell is biased differently. And I will show you an example just now. So here is what we have done. We've taken this cell, one of this cell, and shine light onto it and vary the load, external load, like this. You can change this load. If you make this load open, it becomes open circuit. If you make R0, it becomes short circuit. And then if you put R different values, then that is current is flowing IR, and that will be IV IR drop across this is also the voltage across the diode. Okay, and so different parts we take this PL image. So you apply, you change this load resistance and keep on taking images as the current gets attracted from the cell. So like we said, close to short circuit, it should be black because all the carriers are being extracted and nothing is recombining inside. At open circuit voltage, it should be the brightest. But then in between, you have this scenario, and then you get a PL intensity versus voltage curve, which looks very much like an IV curve. So, and this is not surprising because the current which is going through the diode, a fraction of that only is giving rise to luminescence. So in some sense, what you have done by taking the PL intensity is you are saying this is my IV, typical IV of this curve. Now, why is this advantageous? This is advantageous because if I can get this IV for each pixel, you know, I have this big solar cell. Oh, sorry. If so normally if you connect a current and voltage, you will get the IV of this whole cell. But now, depending upon my pixel size, which is essentially my camera, for each pixel I can generate this IV at each part and then see how different the local IV is. And from that I can say, oh, this part has a high series resistance, so I must do something to fix this. Or this part has a low current, so I must do something to fix this. So it's a great diagnostic tool, and that was the purpose of this slide. So we can extract various parameters. Like here is an example. I won't tell you how, won't give you the details, but I'll just present some results. That here is a cell at some open circuit voltage, and now at each pixel, I did this local IV, if you like, and I mapped the series resistance at each part, and you can see when it is red, in all these regions, the series resistance is low, and here the series resistance is these edges is high. And okay, so you say, okay, you have learned what to do with this. This has to do with how you heat treat the sample, how you heat treat the contacts. And so by optimizing the firing, I can, without having to actually make cells, I can actually quickly measure. So I have got now, if you like, series resistance at every part of the solar cell and the open circuit voltage at every part of the cell. And you can see here the open circuit voltage is large. That must be because my lifetime is large. Whereas if it's a very good cell, like a 19.4 efficiency cell at NCPR, you can see the whole thing is nice and uniform, which is how things should actually be. Okay, so I see I have I have most of it in. So I'll just spend let me see. Prof.S.Sankararaman, how much more time do I have?
15 minutes, sir.
Okay, all right, that'll be done. So all this time we have been talking of shining light to create excess carriers, create electrons and holes. But I told you also, if it's a PN junction, if I forward bias it, I will inject. So if I have an N plus P junction, and if I forward bias it, electrons will be injected into the P. P has full of holes, and if you inject electrons, these electrons are minority carriers. They will recombine exactly the same way as it happened in the photoluminescence. So here is an alternate way of doing the experiment. is to do electroluminescence, which means you bias it in the dark, and then in the dark, you inject minority carriers, electrons into the p-type. These electrons will recombine with holes, and you will get essentially the same kind of images. Okay, so here is an image. So here is an electroluminescence image. I took the cell and I forward biased it, and of course I get luminescence. But there are some regions which are rectangular and rectangular regions. And if I now do a photoluminescence of the same sample, I don't see these rectangles. What is this due to? This is because these dark regions are coming because I am dependent on current reaching there to inject minority carriers. But if the finger is broken, for instance, then it is open, current will not flow, and so you see this broken fingers very easily in a EL image. And this is of great importance. You printed it, you made the cells, and now you want to see how good the cells are. You can't do it under a microscope, but the moment you do an EL, immediately you will see the contrast is so easy to recognize. I have so many broken fingers. And for quality control, you say, if I have more than 5 broken fingers, reject. In PL, I don't see this. Why do I not see this? Because PL, even here, when I shine light, I will create electron hole pairs. So everywhere it is, I will create those electrons and holes. So by looking at the EL and PL, I will say this region was dark, not because of a low lifetime, but because of a broken finger. On the other hand, there is this region, which is dark in both images. This is a low lifetime region of the sample. So by doing EL and PL, this is an example of what you can actually do. All right. Here is a particularly bad case. Here is a sample where you did the EL of the sample. You can see this whole thing is dark. Now we don't know whether there's a problem with the contacts or whether the material is bad. So what you do a PL. In the PL, you don't see it dark. You see it light. So that means this is not a low lifetime region. And now, if you take current out of this, you have force some current. Of course, here this will continue to be black, but in here, optically, these carriers which are generated cannot flow out of the circuit because of the large series resistance. And so you know that this is due to some firing pattern in the metallization, and now you can optimize your metallization firing to get rid of this and make it nice. Okay. All right. So EL complements PL in some sense. Now here is a module. So this is now very important. When I go to a field, when I go to a installation, I have many modules in the field, and I want to know some things. The power has dropped. So if you do a EL in the field, it's very difficult to do PL. I can do EL, electroluminescence, because I just have to use the power supply and do forward bias. When I do that, I see pictures like these, and that means I have cracks. So you see there are small cracks here, major cracks here, and when you have cracks like this, and of course some bright regions here, so these cracks are what are responsible for the power. It affects power output. And for if you are, so here is another such example. Now this is actually has become very important even financially, because what happens is the module manufacturer, when he makes the modules, for every module he will take the EL image as a part of quality inspection, and then he will put it into a ship and send it to wherever, and when you receive it at the other end, you take the EL images again of these same modules, and if it is different from what the manufacturer had, then you say, well, if it has suffered damage, okay, now you can call the shipping company and say, you have spoiled my module, I have not even installed it. And then, so you can get your warranty for warranties back. Sometimes you may have, it may be okay when you receive it, but then when you install it, the installer was not very good. And so when you take a EL image after installation, if it has gone bad, then you catch the fellow who installed it. So monetarily, this has become very, very important. Okay. All right. And so this is one extreme example of a module. One cell is not active. So if you do the EL, every thing is bright, and here is one cell which is dark, and so you can figure out which is good or not. And in the field, this is very useful to do. You don't know which module is responsible for the power breakdown. So if you do this EL and then say, okay, all these modules I will send back to the manufacturer and I can replace and get my money back. Okay. So, well, I have said whatever I have said. After a module is manufactured, EL images of each module are captured. And after each stage of after transportation, installation, you find out if there's any damage, very important for warranty, reinforcement, and periodic EL image gives the health of the module and hence the health of the whole PV array. Okay, so I will conclude with that. The PL intensity is a measure of the excess carrier lifetime in semiconductors. PL imaging has this advantage. I can do it without contacts. I can do it at different stages of processing, and I have given you some examples. PL imaging of finished cells can be used to get an idea of local properties like ideality factor, series resistance, and even local efficiency inside the cell. And if you combine it with EL, you get a very good idea of what is happening in the material. It's very useful in the manufacturing line and R&D process. Okay, that brings me to the end of this talk.